about how we solved a very specific problem in Coq with eGraphs, and perhaps some learnings that everyone can take away from this. So to get us all up to speed, I'm just going to quickly introduce Coq in 60 seconds. For those of you that know Coq, you may skip the next minute. Coq is a constructive proof assistant that is interactive, meaning that at every step of the proof, the user gets direct feedback from the proof assistant about what their current goal is and is then able to manipulate said goal and move ahead in their proof. Coq also has built-in automation that is a brute force search. Effectively, you tell it a set of lemmas and it will try and apply that lemma in any order to hopefully resolve the goal. This is very exponential and very slow. But this is, of course, a problem that not just we have, but everyone else. So there's also a tactic language that sort of is able to take into account the context that a current proof state is in, and you're able to perform proof search. Though in practice, this tactic language is kind of hard to work with and also sometimes very slow. For this talk, also important, Coq is very good at working with inductive data types. So why do we want to combine Coq and eGraphs? Why does this make sense? eGraphs are very good at intelligently finding equivalences. If you give eGraphs a set of rewrites, the eGraph is very likely to point out to you that certain terms are equal, whereas Coq is very good at actually checking and validating those equivalences. There are no guards in an eGraph on whether your equivalences are actually correct because nothing checks your underlying lemmas. So then eGraphs can produce a proof term as well via proof explanation, which sort of gets us closer to the shape that Coq would like to have a proof in. Specifically, Coq is usually quite verbose and needs very explicit instructions, sometimes even with a bunch of arguments to apply a certain lemma within the context that you're in to really understand what you're trying to do. But on the other hand, Coq does ensure that your proofs are valid. So what we can use this for is also to catch bugs in our eGraph code. In fact, while coming up with this presentation, I caught that I had a typo in my eGraph, which I probably would have never caught if not trying to do formal verification. eGraphs are also less expressive than proof assistants. We've seen at length today how it is kind of hard to encode a full lambda calculus style language within an eGraph. Therefore, working with an entire proof assistant language, which usually is based around a lambda calculus language, is hard. Our conclusion from that was try to encode a DSL, which is embedded within a proof assistant, and reason over that. But we'll have a talk later where we're going to see a bit more of a general approach to this problem. So for our approach, let me set the stage a bit. We're using two libraries. One of them is called Vicar and one of them is called Visix. If you've never heard of them, that's expected. They are formalizations of symmetric monoidal categories and the ZX calculus, respectively. For now, we can sort of gloss over what these means, and if you've never heard these terms, you're going to be completely fine in the rest of this talk. But what we need to take away from these libraries is that they fundamentally work on graph-like structures. The problem being, Coq doesn't really do graphs. There have been proofs about graph theory in Coq, but usually those work on axiom-based graphs, whereas we want actual semantic elements that are graphically encoded, and that turns out to be very hard. So what we did is our two libraries formalize symmetric monoidal categories and ZX calculus respectively in an inductive fashion. And to do that, we used a bunch of dependent types, which will become relevant, and it caused a lot of structure because when encoding symmetric monoidal categories we saw earlier, there's sort of these composition operators floating around, and those will be a problem. Let me quickly give you a 30-second introduction to ZX calculus. It's a graphical calculus for quantum operations. You do not need to understand quantum computing for anything that I'm going to be saying, but pretty much we're representing these operations as diagrams. So down here we've got one of these example diagrams, which is in fact cyclic, so it's not just a tree or a DAG, it's in fact a cyclic graph with two color nodes. The nodes are called spiders, so if I say spider, think node. We don't really need to go too much into detail on what the colors are, but this is sort of what a general ZX diagram looks like. And now let's look at Visix. So we take a ZX diagram, so this is a example ZX diagram that I came up with. And we see that it has 3 inputs and 2 outputs, so the inputs are over here and the outputs are over here. And to start encoding this into a proof assistant, what we do is we sort of pull it apart and split it into its components. Then we make each of these components a little subdiagram with a unique number of inputs and outputs assigned to each. And then we start grouping. So for example, we could group the bottom 2 subdiagrams together and then create our little pillars up here and then wrap those together. And now we've sort of got a kind of symmetric monoidal category looking thing that has explicit structure, and we sort of can tell the proof assistant how these elements are positioned relative to each other within sort of this 2D space that we're seeing. And this is completely valid, but we can also go back and do this again. But this time we combine our diagrams like this. This is also a 100% valid representation of the diagram, semantically completely equivalent, syntactically different. And there's also this last representation that is also valid and also semantically equivalent. Now this is a problem because we have quite a few lines of code. So we actually went ahead and measured this. About a quarter of our code just deals with rewriting those semantically equivalent diagrams into each other because of this structure. One immediate thought is, what if we find a normal form? That's sort of a trickier problem than it seems, because during proof you sometimes want to word your lemmas in a way that isn't necessarily conducive to a normal form. Also in the normal form, Coq might not realize that some diagrams are subdiagrams of each other, and rewriting becomes hard. So somehow we need to be able to rewrite the structure. And before we look at how we actually solve this, let's look at what these structural manipulations are. So for one, we have standard associativity for sequential composition, or as we call it, just composition. And also for parallel composition, or as we call it, stacking, with one little addition. There are these little new boxes, and those basically convince the dependent type system of Coq that they are of equal type. Basically, these are functions that carry the dependent type information from one expression to another with an equivalence proof. And then we have some identities both for composition and for stacking. And then we deal with wires. So wires are basically identity operators for composition, but we need to be able to somehow reason about putting a bunch of wires on top of each other, or how empty things or singular things relate to wires. And lastly, we have some rules on casting. Casting is this idea, again, of rectifying the dependent types. And so if we cast the diagram to the dimensions that it already has, the cast just goes away, as seen on top here. Or if we have multiple casts, we can, as we say, contract them and just make them one cast because of the transitivity of proof. Our last and probably most interesting property is distributivity. We've seen this earlier. This means that for this grid of diagrams, it doesn't really matter whether you first compose them or first stack them and then compose them, as long as the dimensions at the points marked are equal, such that these are still valid diagrams. Now let's finally use egglog and talk about how we address this problem in EGRAPHS. So first of all, here's some more not egglog code that describes our dependently typed type in Coq. And I know this looks like a lot of syntax right now, but I'm going to walk you through it. So first of all, we have just some elements here. Those are our base elements, like the spiders, or the very base elements, and then we have stacking composition. And what we do at first is we just completely ignore the fact that dependent types exist, and we translate this into a type in egglog, where we have our basic generators, we have composition, and we have stacking. Now, egglog is not a dependently typed language, but we need to have dependent types. So what we'll do is we'll sort of encode our two dependent type arguments as functions and sort of flip the problem on its head. That instead of assigning sort of giving the dependent type as a parameter to an object, we compute it backwards from an object. Meaning that, for example, for the generators, we just simply take their dependent type arguments and return them from these functions. So that is the very basic case. And for example, for wire, my clicker is not working. Wonderful. For wire, we can we simply define ourselves this as a basic generator, and then it will provide the dependent types that we expect through the functions zxn and zxm. For stacking, this also kind of works as you'd expect. We simply add the dimensions of the two subdiagrams together. But where it gets a little more interesting is for composition, because we want this function to be effectively partial, such that it only returns a value if the diagram is valid. We don't want to give dependent type information on a diagram that shouldn't have dependent type information, because it shouldn't exist in the dependently typed context, even though we're able to express it with an egglog. And what we do for that is we first specify the overall input and output type sort of in the way we'd expect. And then we add this check to ensure that the inner dimensions actually match to make this function partial. And with this partial function defined now, we can look at how we can take a lemma from the world of Coq and in our DSL into this context of egglog. So we're looking again at our example of distributivity. On the bottom here, there is a little bit of Coq that expresses this formally. And when reading this, the left-right arrow means composition, the up-down arrow means stacking. It basically just says what is in the diagram. In fact, this diagram is automatically generated using our visualization library from the term below. And if we now want to translate it, we sort of do this backwards approach again, like we did with the actual data type. First, we translate the actual statement of the lemma while completely ignoring dependent types. So for any diagram where now the dependent type information would be correct, this would produce a correct rewrite. But of course, for any diagram where the dependent types on the composition do not work, this would produce an invalid diagram. Therefore, we need to analyze the type information and find out which diagrams have equivalent types at what point, and then automatically generate these conditions that ensure our diagrams within our eGraph rewrite system in fact respect this dependently typed constraint. And overall, the way this works is we take out the type information and the lemma from Coq, then we convert it into a Python IR that does pretty much exactly what we just did on the whiteboard, where it splits into the separate rewrite statement and the type information and then produces the egglog code with all the necessary checks. And the reason this is sound is because we again have this partial function that for valid diagrams gives us this information. So if we have an invalid diagram, all of these checks would fail right out of the gate. Now we've heard a lot about eGraph blowup with similar diagrams in the morning, and there's also a paper on how modulo AC, meaning associativity and commutativity rewriting, causes eGraphs to grow in size pretty much indefinitely and never terminate. But we're able to sort of skirt around a lot of these problems. First of all, we don't have commutativity. So in the morning, in the symmetric monoidal category talk, the main culprit of the blowup was being able to commute partial diagrams through the swap or braid operator. We do not have any of this, as this is a bit more intensive in Coq, and we're really just dealing with the structure. So we're rewriting really modulo AD, which is associativity and distributivity. Then the other problem field is when we do stack associativity, we introduce this new term around the stack that then is immediately rewritable with the other associativity rule. But because we have cast contraction, this is also a problem that we avoid, where otherwise we would have infinite growth of the eGraph. And then lastly, a problem that comes up in modulo AC rewriting is that you often have to add identities somewhere, increasing the term size. If we include the identity addition into our project, this will also blow up and not terminate. But we're able, for most rules in our system where we have the identity in there, we're able to replace that identity with diagrams that just have a single output, like we see down here. And I realize I flipped this, so just imagine it's mirrored in your head. But if this has a single output, like an identity, then we're able to completely avoid the problem of carrying identities around. We're able to just remove identities. In fact, we don't have a formal proof yet, but we have a strong conjecture that if we normalize rules to this form, that we shouldn't ever run into a problem where we have to add identities, and in practice we haven't found one yet. So let's look at an example of how we can use our system to rewrite a problem that we have in practice. So this is taken straight from our library. This is a structural rewrite that we had to do at some point in our code, and it may not be immediately obvious, but these two diagrams are in fact equivalent, because all we do pretty much is we split up this identity here and then reassociate a bunch of times until we hit the left side. And below this, I put in the cock proof. It's not necessarily super long. It's about 3 minutes of development time, but about a quarter of our entire library is just dealing with these problems, so it becomes incredibly repetitive and is a real slowdown for working with our library. Now, if we do this in eGraph land, what happens is we get this beautiful diagram that I chose to not make bigger so people don't actually try to look at it too much. But the search completes within less than half a second, so pretty much instantaneous. And even compared to cock automation, this is very fast, and we're quite happy with it. Now, you may have noticed this work is an egglog, and for those of you that know egglog a little better, egglog doesn't yet have proof production, meaning right now the proof terms, or sort of the equivalence check that we have, isn't actually ported into cock yet. However, there is previous work by Andrei Kozyarev that uses egg proof production to rebuild cock terms, and we will be using his work and sort of adapting it to our tool to build back the proof terms into actual cock. And this is the eGraphs workshop, so I think you find eGraphs interesting, and this is a very big tangent, sort of about, can we do proofs just like plainly in eGraphs without having an underlying proof production system? And the answer is sort of. So instead of rewriting in the eGraph, we can always introduce nodes that relates to terms. For example, if we have A equals B, we add a node that says there is a path from A to B, and then we can sort of build the reflexive transitive closure over those terms. The problem why I'm saying sort of is that this blows up as soon as you have binary operations. So consider the following example. We have A equals B and C equals D. Then A plus C equals to B plus C, A plus D, or B plus D. Now, when building the closure, we want to ideally know which one should we pick. And naively, of course, we would pick the one that carries the most information. However, we don't really know what our proof in the end will look for while building the eGraph. And therefore, we need to build all of them. And that means we have exponential growth over binary operators. And in a system with a ton of binary operators like ours, that will make it unusable. All right, returning from this little anecdote to future work. As I previously said, we want to build full interfacing with cock once the proof explanation system exists in egglog. We want to add the support for users to pass in their own lemmas. This is also why we built this automatic lemma translation, so that a proof engineer is able to pass in whatever lemma they think is useful for right now automatically solving their goal. This will, of course, lead to some problem instances where the eGraph won't be successful, but it would be really interesting to see how complex of problem classes we could actually tackle in practice, and what kind of code automation we could achieve from that. So with that, sorry, one last point. We also want to get truly non-axiomatic graphical reasoning, which means that we want to have a way to reason about graphs with semantics and calc without actually having to worry about structure. And this is sort of the first step towards it. With that, a quick summary. We're using eGraphs to work on a formal verification library called Visix, where structural rewrites are a problem. So we looked at our class of rewrites and built automatic lemma translation so that we can deal with them, and we're hoping to use egglog proof production soon to reintegrate this into calc. Thank you so much for your time.
All right, thanks so much. We have time for maybe one question while the next speaker goes ahead and gets set up. Any questions?
Thanks. Thanks, really cool stuff. So I was curious, because you're talking about the difference between egg and egglog, what the particular part of the data log extensions is that you need for your use case. So why couldn't you use this interfacing with egg in calc?
Yeah, that's actually a very good question. Let me just go back a couple slides for that. So when we deal with these functions that are defined in the eGraph, the data log makes the lookup of that much faster and be much easier to state. So that's really, this part is where we use the data log features.
Okay. So it would be in principle possible, but it's easier and faster.
It is easier and faster, yes.
Okay, cool. Thanks.
Okay, thank you so much.
Thank you.